Okay, the five-step procedure for developing a model. Step one, hypothesize the deterministic component of the model. So do we want to use a simple linear model like ax plus b, or do we want to use something not as simple, for example, ax squared plus bx plus c, whatever, or do we want to do an exponential relationship, whatever you choose the model. So hypothesize the deterministic component of the model, and that you would do from kind of deep knowledge of the subject. Use the sample data to estimate unknown parameters in the model. 3. Specify the probability distribution of the random error term and estimate the standard deviation of this distribution. 4. Statistically evaluate the usefulness of the model. And 5. When satisfied that the model is useful, use it for prediction estimation and other purposes. All right, now, fitting the model. We talked about the least squared approach. So let's see. To begin with a simple example, paragraph 2 here. Suppose an appliance store conducts a 5-month experiment to determine the effect of advertising on sales revenue. The results are shown in the table here. So month 1, advertising was 1, sales revenue was 1. Month 2, advertising was 2, sales was 1. Month 3, advertising was 3, sales was 2, and so on. We have this data. The number of measurements and the measurements themselves are unrealistically simple in order to avoid arithmetic confusion in this introductory example. This set of data will be used to demonstrate the 5-step procedure of regression modeling given in the section. In this section, we hypothesize the deterministic component of the model. We hypothesize the deterministic component of the model and estimate its unknown parameters, steps 1 and 2. The model assumptions and the random error component, step 3, are the subjects later on. Step 1, hypothesize the deterministic component of the probabilistic model. As stated before, we will consider only straight line models in this chapter, thus the complete model to relate mean sales, expected value of y, to advertising expenditure x is given by E of y equals just the linear model there, beta sub 0 plus beta 1x. Step 2, use sample data to estimate unknown parameters in the model. This step is the subject of this section, namely, so remember, basically, we're going to use the least squares, ordinary least squares method to estimate. We saw how to do this before, but I'm going to review it again, to estimate beta sub 0 and beta sub 1. To determine whether a linear relationship between y and x is plausible, it is helpful to plot the sample data in a scattergram. Okay, so let's do that. So there it is. We plotted the data that we had just seen. Here's the plot of it. Note that the scattergram suggests a general tendency for y to increase as x increases. If you place a ruler in the scattergram, you'll see that a line may be drawn through 3 of the 5 points, like that. To obtain the equation of this visually fitted line, note that the line intersects the y. Okay, so we could get the equation by some other means, but that's not really how we do it. One way to decide quantitatively how well a straight line fits a set of data is to note the extent to which the data points deviate from the line. For example, to evaluate the model in figure 9.4, we calculate the magnitude of the deviation. So you can see actually that there are only 2 deviations for that particular line. These deviations or errors of prediction are the vertical distances between observed and expected values. The observed and predicted values of y, their differences, and their square differences is shown in the next table. Note that the sum of errors equals 0, and the sum of the squares of the errors, which is SSE, sum of squares of the errors, which gives greater emphasis to large deviations of the points from the line is equal to 2. Let's see that. So we calculate, here's x, here's y, oops, there's y. This is the model that we're proposing here, y hat or y bar. These are the predicted values, in other words. And then these are the deviations from the predictions. So remember, we said 3 points lie on the line, so there's no deviations for those points, or there's 0 deviation for those points. And there's some other deviations for the other points. So we have 1 and -1. And then over here, we're taking the square of the deviations here. And so we get 1 squared is 1, and -1 squared is 1. So the sum of the squared errors, SSE, equals 2. Okay, so please take note of SSE, the sum of the squares of the errors. Now, if the they make an observation up here. They say that if the error is larger than 1, then when you square it, you're going to blow it up, right? So they say that it gives greater emphasis to large deviations. You can see that by shifting the ruler around that the graph that it is possible to find many lines for which the sum of errors is equal to 0. Okay, so in this case, our sum of errors was equal to 0. Notice that the 1 and the -1 up above there canceled to give us 0. And this is going to happen with many lines, not just the line that we happen to choose. But it can be shown that there is one and only one line for which the SSE is a minimum. And with the sum of the squares of the errors, we want to find the line which makes that minimum. This line is called the least squares line, the regression line, or the least squares prediction equation. The methodology used to obtain this line is called the method of least squares. To find a least squares prediction equation for a set of data, assume that we have a sample of n data points consisting of pairs of x and y values, say x1, y1, all the way up to xn, yn. For example, the n equals 5 data points shown in table 2 are let's see that. So 1, 1, right? 2, 1, 3, 2, 4, 2, 5, 4. Over here, the last one was 5, 4. There. Okay, the fitted line, which we will calculate based on the 5 data points, is written like that. All right, now, okay, y hat, beta 1 hat. Why did they write beta 0? I'm sorry, beta 0 hat and beta 1 hat? Well, the y hat is clear. We already talked about that. We're only going to get estimates for beta 0 and beta 1 because those are from the population, so we can't know those. For a given data point, say the point x sub I, y sub I, the observed value of y is y sub I. That's the y sub I there. And the predicted value of y would be obtained by substituting x sub I into the prediction equation. Okay, I think we already discussed that. And the deviation of the ith value of y from its predicted value is y sub I minus y sub I hat, right? That's what we mean, right? The deviation of the ith value of y from its predicted value. The ith value is y sub I, and the predicted value is y sub I, y hat sub I. So the deviation is that. But we can write that as y sub I minus what we wrote up above as y I hat. So we just substitute that in, and we get this. We get this. Well, we get that. Then the sum of squares of the deviations. So now the sum of the squares of the deviations of the y values about their predicted values for all the points. So if we want to add them all up, we want to square these and add them up, we write it like that. So SSE again can be written like that. The quantities beta sub 0 and beta sub 1 that make the SSE a minimum are called the least squared estimates of the population parameters beta 0 and beta sub 1. And the prediction equation is called the least squares line. So we don't know what this beta sub 0 is and what this beta sub 1 is. Beta sub 0 hat and beta sub 1 hat are. We want those which will make SSE as small as possible. The least squares line, y hat, is the one that has the following two properties. One, the sum of the errors, SE, equals 0. We saw that. We want the sum of the errors to equal 0. But we'll get that for many lines. And two, we want the sum of the squared errors, SSE, is smaller than for any other straight line that we could draw in there, or any other straight line model. The values of beta sub 0 hat and beta sub 1 hat that minimize the SSE are given by the formulas in the box. So they're going to tell us how to calculate beta sub 0 hat and beta sub 1 hat. And they're not going to tell us how to prove that this does give us the smallest SSE. Let's see, where is that box? Here. Now, how are we going to calculate the beta sub 1 hat and the beta sub 0 hat? From the data. It better be from the data because that's all we have. So I can see here that beta sub 1 hat is SSXY and divided by SSXX. Now, we haven't talked about what those are. But whatever they are, they better come from the data because that's all we have. So somehow we're going to get a formula that's going to allow us to take the data and get the beta sub 1 hat and the beta sub 0 hat. So it looks like we're going to need to know what SSXY and SSXX are. So here's SSXY and here's SSXY. All right, let's stop here.